Hello, and welcome to another episode of The Science. Today we are here to discuss pixel mapping. Pixel mapping is the process of mapping a video or photo onto a light or an array of lights to create interactive lighting. It uses specialized software to send the RGB values of each pixel to the light. It's the process we use when we employ image-based lighting. Pixel mapping breaks down into 3 steps. Step 1, patch the fixtures, selecting the correct DMX profile. Step 2, build your array of light fixtures into the correct quantity and configuration. And step 3, send the media to the array. The pixel mapping engine, or media server, builds a grid over your lights. Then when the video file is played back on the grid, whatever color is rendered in that block, the system sends that RGB data to the corresponding pixel. And it does this for every pixel that it renders. When a light is controlled from a lighting console, it is assigned a DMX profile. This is the collection of parameters used to control the light: intensity, color temp, hue, saturation, and so on. The DMX profile is set on the light and then patched into the lighting console as that profile. When pixel mapping, each pixel will need a set of these parameters. This is called a parameter channel group. This will allow each pixel to act as its own light fixture. There's a link below describing how the parameter groups are set on the Rainbow 2 and Double Rainbow. As you already sensed, this means you'll be using up a whole lot of data. For example, the Q100R2, the 8-foot Rainbow 2, has 48 pixels. Say we have 5 DMX channels per pixel, like in Profile 1. Suddenly you've used 240 channels for one light. As we all know, a DMX universe only contains 512 DMX channels. So in this configuration, we can fit 2 8-foot rainbows in a universe. So you have to be cognizant of your network capabilities. It's possible you won't need as detailed of a pixel map, but generally speaking, the greater control and detail, the better. Fortunately for the Rainbow series lights, they can use just about every wired data protocol: DMX, SACN, and ArtNet. So you can best decide how to manage the network. It's a decision you will have to make depending on the scope of your project. Most pixel mapping engines utilize only RGB in 8-bit or 16-bit. So when selecting fixtures for pixel mapping, be sure that they have compatible profiles. However, there are more lighting considerations than just RGB. More advanced DMX fixture profiles for pixelated lights will have global parameters. Global parameters are groups of channels at the end of a series of pixels that apply to the entire light fixture. When RGB are all at 100%, the color that is produced is white. Well, what is the color temperature of that white? What is the tint, or plus and minus green? CCT and plus and minus green are both global parameters. Another consideration for pixel mapping is the media. Those are the assets you will be mapping onto your lights. The media will already be transcoded into a specific color space. It's important to test the color of the assets you will be using for pixel mapping. As you may know, there is no real standard yet for these color spaces. And if the color space of your lights differs from the color space of the media asset, you'll be stuck with artifacts that do not represent the correct color. Those discrepancies will appear when you test your lights. If I load up this flame video that is transcoded in Rec. 709 up on the LED wall, it renders correctly as the color space for the wall is Rec. 709. If I then load up the same Rec. 709 video onto the lights directly in a traditional RGB profile, there will naturally be color fringing on the lights. This is because the lights are expecting a generic color profile. So if you test your media and find that your assets are in the wrong color space for your production, you basically have 2 options. You can transcode the media into the correct color space, or in the case of the Rainbow series lights, there's a DMX parameter to change the color space on the fly. Color space of the incoming RGB is another global parameter. For the Rainbow series, we also have spectrum control and output mode as global parameters. Check the links below for more on these features. For patching this rig of 48 of my 48 pixeled Q100R2s, I'm going to set them into my VRGB profile, Profile 64. This profile is 48 cells of RGB at 16-bit and my global parameters of CCT, plus and minus green, spectrum, color space, and output. Okay, so we've set our color space, chosen the appropriate parameter groups, assigned our global parameters to more easily affect control, and patched our lights into the console with the correct profiles. So back to the 3 steps of pixel mapping. Step 1, patch the fixtures, selecting the correct DMX profile. Step 2, build your array of light fixtures into the correct quantity and configuration. Let's dig into that. So over here on my rig of Q100R2s, I've already patched them into the console. Next, I'm going to place them into the correct configuration. I will want to build the pixel map to accurately reflect the rig of lights. The pixel map is a 2-dimensional grid that lies on the XY axis. Don't confuse this XY with those that represent the color coordinates in an XY profile. So for my rig of 48 Q100R2s, I will build an array 48 across and 48 down. That is a total of 2,304 pixels. My Geminis are a single pixel each. My 406 Osmium array with 6 double rainbows will be 24 pixels across and 12 down, and on and on. You can make individual pixel maps for each one. Here we get to decide what part of our asset to use, where to use it, and how we might want to manipulate it. We decide what images to incorporate into our IBL. So let's get to step 3 of pixel mapping, sending the video to the lights. When pixel mapping, each piece of media that you are playing back is separated into its own layer. Each layer can play back on one array or many arrays. It all depends on how you configure it. Each layer can be manipulated and stretched with parameters like position, scale, and speed. Once those are set, hue, saturation, exposure, and many more parameters can be changed. We are using a volume wall to set the carnival scene behind me. In order to enhance the look of this carnival, I will be putting the Ferris wheel into the Q100R2 rig to play out on this side of our set. Above, we have another array of Q100R2s, which are mapped to the fireworks launching into the sky. I've set a couple of Geminis to act as our back or clarity lights and mapped them to the blinking lights of the ride. In the front, we have a 406 double rainbow array as our key or contour light. I'm going to map this to another section of the ride. So here on my monitor, you can see what portion of our assets are playing on which lights. And if you look at the set, you can see how image-based lighting plays out. Our images are going through the rainbows and Geminis and are in sync with the images playing through the volume wall. And you can cherry pick what part of the asset you want to play on which light to get your desired effect. It's pretty cool. All right, so now that we have selected the media and manipulated the layers into each light, we'll take down our Gemini key and take a look at the close shot, framing out our lights just to simulate pixel mapping. Now let's compare this setup with traditional lighting. We will take all the video files out of the lights and simulate the environment with cues from the console. Programming in each blink of each light took much longer to create for this look. As you can see, the lighting still looks decent, but it's not as animated and active, and the colors are close but not the same as the LED wall. And most importantly, it's not as believable that our actor is in this environment. Let's go back to our IBL version. Much better. So now you have a taste of how pixel mapping for image-based lighting goes. And as you can see, it plays an integral role in virtual production, really enhancing the look and feel of volume environments with spectrally full and color-correct lighting. And it can artfully add a new layer of depth and energy to just about any traditional lighting scenario. Thanks for joining us today. We have a lot more information in the links below. As always, be safe, and I'll see you at Crafty. Scene 1-9, take 2. Scene 9.
192-34. From the top.
Top! That was a good one, huh?